have covered DC machines and the transformers and some previous year questions. So in this lecture, we'll start with the induction machine. So let's see the what are the topics available in the induction machine. First, we'll talk about the basics of induction machines like the construction and the working principle. And then we'll talk about the induction machine equivalent circuit, like how to derive the equivalent circuit. And thereafter, we'll be seeing the power flow equations and the torque versus slip characteristics. And then we'll talk about the induction machine losses and the different types of testing methods. And then we'll talk about the starting methods of an induction machine. Finally, we'll be having a speed control. So, so induction machine operates in two modes, mainly generator mode and the motor mode. Induction machine operates in generator mode as well as motor operational mode. So the speed of an induction, so in motor operation, the speed of a machine is always less than the synchronous speed, whereas this in case of a generator operation, the speed of an induction machine is always greater than the synchronous speed. And there is no constructional difference between the generator as well as a motor in induction machine. An induction machine is also called as an asynchronous machine because it runs at a speed other than the synchronous speed. So induction machine has shunt type of characteristics that is similar to that of a DC machine. So where we call the DC machine as a constant speed machine. So we'll see that later on why the induction machine has a shunt type of characteristics. And the induction machine is the most popular motor because it has less number of components. Uh, and it is also more, as far as induction generator is considered, it is mostly widely used in wind energy conversion. So let's see the differences between the transformers and the induction machine. So earlier class we talked about the transformer. So what are the differences between the transformer and an induction machine? So transformer is not an energy conversion device, right? I mean, if you see externally, so electrical input, electrical output we are getting. But if you see internally, energy is converted to magnetic energy and then back to the electrical energy. So talking with respect to the electrical input and output terminals, so transformer is not an energy conversion device. Whereas induction machine, is an energy conversion device. Because if you take an induction motor, it converts electrical energy into mechanical energy, whereas induction generator will convert the mechanical energy into the electrical energy. So it is an energy conversion device. In transformer, the no load current I naught earlier we have seen, right, is around 5% of full load current. Whereas in induction machine, generally the no load current will be very high because there will be an air gap. Current in a machine is high compared to that of a transformer. Transformer is a constant frequency device. So whereas induction machine is a variable frequency device. Induction machine runs transformer is a stationary device, right? So both windings are stationary, whereas in a stator winding is stationary, whereas rotor winding is the induction machine is mobile. It has a rotating component, so the losses in induction machine is more, or the efficiency of an induction machine is less when compared to that of an transformer. Okay, we'll go to the next slide. So this is what we have seen in the earlier slide. Spaced by 120 phase winding. These three windings displaced physically from each. Second condition is current flowing through these three windings should have a time angle displacement of 120 degrees. That means the three phase waveform. See, this is phase A. After 120 degrees, we should have the phase B, and then we have the phase C. So whenever a three phase currents having a phase angle time angle displacement of 120 degrees passed through in a three phase winding having a physical displacement of 120 degrees, we will be getting a rotating magnetic field in the air gap. Generally, the expression for this rotating magnetic field is given by F R equal to T by 2 Fm cos omega t minus theta. So, for example, let's say we have two poles here. So, this is one conductor, the other. So, here we have cross, here we have dot. The coming out, current is going away. So, if you for this machine, generally, if you take the this is how the waveform looks like, MMF waveform, right? So let's call this angle is, let's say this angle is theta. Now from this expression, if you clear that, with respect to the time, the MMF wave keeps on rotating at frequency. We'll be getting a rotating magnetic field. We know that the sinusoidal current pass whenever sinusoidal current pass in a three-phase winding, we'll be getting a rotating magnetic field, and whose magnitude is given by 3 by 2 Fm cos omega t minus. So, and it rotates with a synchronous speed. So this is for a three-phase system. Suppose if we have an M-phase system, then resultant magnetic field can be given by M by 2 Fm cos omega t minus theta. This also rotates with synchronous speed. Now, producing the RMF with two-phase display, two-phase system, physical displacement between the two windings should be 90 degrees, and the current flowing through should have a time angle displacement of 90 degrees. Synchronous speed is given by ms equal to 120 f by. And let's go to the next slide where we'll be talking about the construction of an induction machine. So this is what we have discussed in the earlier slide. So based on the construction of a rotor, machines are classified into two types. One is a squirrel cage type, the other one is the wound rotor type. So induction machine has both stator and rotor. So based on the construction of a rotor, we have two types of induction. One is squirrel cage, other one is wound rotor. This is all called as slip ring. So the corresponding machine is called squirrel cage induction machine. This is called a slip or wound rotor induction machine. Based on the construction of a rotor, induction machine is classified into two types, that is slip ring induction machine and squirrel cage induction. So let's go to the next slide. So this is what we have seen in the earlier slide. So now see the futures of wound rotor, futures of squirrel cage induction machine. So here, in case of squirrel cage induction machine, generally the rotor consists of it doesn't have winding. It has copper bars. It consists of bars like this. Yeah. And these bars are connected at the end by means of end rings. This one, this end rings. So here, first point, the rotor is not owned for definite number of poles or phases. So number of poles and phases will be induced on the rotor based on the stator connection. So the same number of poles will be induced in rotor as of the stator. And here the second, generally if you consider a wound rotor, I mean you take a rotor where the winding is wound, generally they have overhang portion. Overhang portion. See, this is the winding, right? Suppose this is a winding. This part of winding is called overhang portion. In squirrel cage induction machine, we don't have the overhang because we are using bars, copper bars. So there won't be any overhang portion. Generally, overhang what happens is it leads to the leakage flux. So since there is no overhang portion here, the leakage offered by the rotor winding is less. The third one is here the rotor surface is smooth. So the excitation current or the no load current is less. The other advantage is the no load as well as the full load operating power factors of squirrel cage machine is good. So, as well as full load operating power factors are good. Good in the sense they are high. So these are the advantages. And then we have the drawbacks. Drawbacks is the rotor impedance is less. So the what happens when the rotor impedance is less? The motor draws a huge starting current. So we need a start. Rotor winding resistance is less. So what happens is the starting torque is also less in case of an squirrel cage induction. We will see the derivation of a torque, how it is a function of the rotor resistance. So there we'll understand. So in conclusion, we can say that the squirrel cage induction motor starting performance is poor, running performance is good. Same poles as stator, less leakage flux, less rotor impedance. So it results in high starting currents. So less rotor impedance. So it results in less starting torque. So let's go to the next slide. So this is what we have seen in the earlier slides. Speaking of the figure of a squirrel cage rotor, where we have the copper bars. They are slightly tilted and then they are connected by means of an end ring. We'll talk about the slip ring induction machine or the wound rotor features. First one, advantage. Here, the wound rotor machines generally are owned for a different number of poles. Here we'll be having a winding. So we having what winding will be placed. So generally they use three-phase short pitched winding. Short pitched winding is owned for different number of poles. So the rotor winding is generally connected in star, whereas of a rotor, whereas for a stator, the winding can be connected in star or delta. Third point. Actually, the rotor impedance is high for a slip ring induction when compared to the squirrel cage. So what happens is it has high starting torque when compared to the squirrel cage induction machine. Here the rotor surface is not so smooth. So what happens is it requires more amount of magnetizing current. So the no load current is more, or you can say the magnetizing current of wound rotor machine is greater than that of squirrel cage machine. Here, since we are using windings, so there will be having a overhang portions, because of which the leakage flux will be high. So for a wound rotor or slip ring induction machine, the starting performance is good because it has higher rotor impedance, so it takes less starting current as well as the starting torque is high. But due to the presence of leakage flux, the running performance is inferior when compared to that of a cage machine, a squirrel cage machine. And one more drawback is here, this is the rotor, right? Here we have shaft. On the shaft, there will be slip rings. Okay, because of slip ring, what happens is maintenance is cost. Slip ring induction machine is greater than that of the squirrel cage induction machine, and the efficiency of the slip ring induction machine is less than that of efficiency of squirrel cage. Okay, let's go to the next slide where we'll talk about the working principle of an induction machine. So if you see here figure, so if you here we have a armature on which there are slots. In these slots, winding will be okay, and these are the slip rings that are mounted on the rotor shaft. Okay. This topic is working principle of induction machine. So we have a three-phase winding. Now we'll give a three-phase supply. So when I say, let's say this winding is delta connected. So we have three-phase supply, and then it is connected to the delta connected winding of the stator. So whenever we are giving three-phase balanced supply through a three-phase winding, so from earlier conditions, There we have seen the conditions to be satisfied for creating a rotating magnetic field, right? So here both the conditions are satisfied. So you'll be getting a rotating magnetic field of magnitude d by 2 m cos omega t minus theta. So what happens? There will be a magnetic field. So this is the stator. So there will be a magnetic field, rotating magnetic field will be produced in the area, and here we have the rotor. So whenever a current is placed in a magnetic field, what happens? An EMF will be induced. Since the rotor is connected closed with closed loops, because of the induced EMF, there will be current flowing through this rotor. So this EMF, this current will produce flux, which opposes the original cause that produced it. So the original cause is the main flux. So what happens? Uh, Machine starts to rotate in the direction of the rotating magnetic field. What happens? Why? Because if the machine starts rotating in the direction of magnetic field, generally the rotating magnetic field rotates at synchronous speed, right? Plus equal to 120 F by P. Suppose if you take a 50 Hz supply, and we have two poles, then we have 3000 RPM. So the rotating magnetic field is rotating at 3000 RPM. So the current is placed inside the rotating magnetic field. So this rotating magnetic field cuts the stationary rotor, because of which an EMF will be induced in the rotor. And due to this EMF, as the rotor is a closed path, so there will be current, and this current will produce flux, which opposes the path. That is the main flux. So means that to achieve that, what happens is the rotor will start rotating in the direction of rotating magnetic field. Uh, so, but it will never be close to the synchronous speed, because when it close to the synchronous speed, rotor speed, synchronous speed, what happens? Both the rotor as well as the magnetic field are rotating at the same speed. So there won't be any flux by the, so there won't be any EMF induced in the rotor, and the induction motor operation doesn't take place. So what happens is, so the induction motor always runs at the speed less than synchronous speed. Now there is one term called slip. Slip. Slip of an induction motor is generally given by S equal to Ns minus Nr by Ns. Nr is the rotor speed, Ns is the synchronous speed. And there will be current flowing in this rotor, right? So the frequency of this rotor current is given by slip frequency. S into F. F is a supply frequency. Okay, let's see some example questions. So this is what we have seen in the earlier slide. So this is a gate 1990. What does the question says? A three-phase slip-ring induction motor is fed from a rotor side. Stator winding short circuited. So the frequency of the current flowing in the short circuit stator is, so earlier we have discussed this point, right? So the frequency of the current flowing in the short circuit stator is slip frequencies S into F. So next question. Three-phase 4-pole 400 volt 50 H squirrel cage induction motor is operating at slip of 0.02. Speed of the rotor flux in mechanical radians per second sensed by a stationary observer is close to. The speed of the rotor flux is generally is nothing but the speed of a rotor. The speed of the rotor flux is nothing but the speed of the rotor. So we know that first try to find out the synchronous speed that is given by 120 F by P, right? So 120 into the frequency is 50 Hz, number of poles is 4. So that is 1500 RPM. Know that the slip equal to Ns minus Nr by Ns. So if you solve this equation, we'll get Nr equal to 1 minus into Ns. So slip they have given as 0.02. So Nr equal to 1 minus 0.02 into Ns, that is 1500 RPM. So we'll be getting 1470 RPM. So the option is D. Okay, let's go to the next question. A 4-pole induction machine is working as an induction generator. The generator supply frequency is 60 Hz and the rotor current frequency is 5 Hz. The mechanical speed of the rotor in RPM. So generator supply frequency is 60 Hz. The rotor current frequency is 5 Hz. We know that frequency of the rotor current to slip time SF, slip frequency, right? So that is equal to 5 Hz. So slip equal to 5 by 60. That is 1 by 4. Now they're asking us the speed of the rotor, right? That is Nr, that is equal to 1 minus S into Ns. Ns equal to 120 F by, so that is 120, frequency is 60 Hz by 4 poles. So that is 800 RPM. 1 minus 1 by 12 into 800. So if we solve this, we'll be getting 1950 RPM. So option C. Let's go. Let's go to the next question. Eight-pole, three-phase, 50H induction motor is operating at speed of 700 RPM. The frequency of the rotor current of the motor in H is I have given number of poles equal to 8, frequency equal to 50 Hz. It is induction motor is operating at a speed of 700 RPM. The frequency, they're asking us the frequency. You know the frequency of the rotor current is slip times frequency, right? First we have to find out the slip. Slip equal to minus NR1 is equal to 120 F by T into T is 8. Into 2 is 15 into that is 750 RPM. So 750 minus NR is 700 by T by 7. Okay. So we got the slip. Once we got the slip, the frequency of the rotor current is slip frequency, that is 1 by 50 into 50. Okay, let's go to the next topic. So here we'll talk about the rotor circuit changes. Generally, the rotor circuit consists of copper bars, resistance, and then, but the current flowing through it is at a slip frequency. Right? Slip times resistance is R, this is Sx2, slip times the supply frequency. Circuit by S. R2 by S can be written as R2 R2 so that is R2 into S minus 1. This is represented as a variable one because machine speed varies, slip varies. So thereby this resistive component varies. The rotor circuit under still condition. Under standstill conditions, the frequency, the induced EMF generated. So induced EMF expression is same as that of a transformer. AP, KD, these are winding factors. So that seen in case of an alternator, frequency into M. Whereas when the machine is running, the induced EMF per phase is slip times that of E. So ER. So this is times U2. The rotor winding leakage reactance X2 equal to F by F equal to a standstill condition. Under rotating conditions, the rotor leakage reactance is given by XR equal to slip times that of X2 because the frequency will change. And the rotor winding impedance Z2 equal to R2 plus J times X2 in standstill condition. And running condition it is ZR equal to R2, it won't change, plus J times XR. And the rotor winding current I2 equal to E2 by R2. Here the rotor winding current IR equal to ER by ZR. slide. What I have discussed in the earlier slide. So what are the differences in the rotor circuit when the machine is under standstill and the machine is under running conditions? Now let's see some of the losses equations in induction machine. So the rotor circuit of an induction machine is given by R2 by S X2, right? This circuit we have modified it as R2 X2 and then a variable resistor, let's say RL. This is E2. Generally, the power transferred to this variable resistor, so the current is I2. That is 3, let's say IR square RL is nothing but the gross mechanical power output of a induction motor. So that is given by 3 IR square RL is R2 into 1 by S minus 1. This is gross mechanical power output. The other way of saying PM. Okay. And the rotor of an induction machine receives power from the stator, right? So that power is called as an air gap power, PAG. That is given by 3 times IR square R2. Okay. So now if you take the IR square R2 by S from this, and the losses in this resistor represent copper losses in a induction machine. So that is given by D IR square R2. So now if you take ratio of PAG is to P copper is to gross mechanical power developed, 1 is to S is to 1 minus S. Say of it, or efficiency of an induction machine, approximately slip time. Okay, let's go to the next slide. This is what we have discussed in the for induction. Yes, the ratio of gross power output to the air gap power equal to. So we know that the air gap power is given by 3 IR square R2 by S. The gross mechanical power is given by 3 IR square R2 into 1 by S minus 1. This is, let's say this is 1. Say this is equation 2. Now they're asking us the ratio of gross mechanical power output to the air gap power. So that is PM by PAG. So that gives 3 IR square R2 minus 1 by 3 IR square R2 by S. So this gives you 1 minus S. So the option is B. Let's go to the next topic, that is equivalent circuit of an induction machine. Circuit, if you look actually similar to that of a transformer circuit, and there we have, so primary we have R1, X1, and then we have the shunt branch parameters XM and RC. Then we have the primary winding. Here we have the rotor parameters, that is R2, X2. Then we have our variable resistor, that is R2 into 1 by S minus 1. Now we have to transfer these parameters to the primary side to get the equivalent circuit. So if you transfer them, then the equivalent circuit looks like R1, X1, shunt branch parameters, C, XM. This is R2 dash, X2 dash, RL dash. This R1, R2 dash is equal to R2 by K square. X2 dash equal to X2 by K square, where K is equal to turns per phase, rotor turns per phase into rotor winding factor kWr, and stator turns per phase into stator winding factor. We can further approximate this circuit by transferring the shunt branch parameters. Before this R and X, primary winding resistance and reactance, then we'll be getting circuit looks like RC, XM, and then we'll having a net resistance RM and reactance XM. Then we have the variable load resistor RL dash. Here RC and XM are the core loss resistance and the magnetizing reactance. So RL dash is the stator referred electrical equivalent of a mechanical load. Let's go to the next slide. We have discussed in the earlier slide. Next, talk about the power flow in an induction machine. How does this, how our equivalent circuit works? Stator, resistance, reactance, and then we have the shunt branch parameters. Then we have our secondary winding resistance, reactance, the load component RL, here we have the stator power input, right? This is the output. Let's say we call it a shaft power. And from this we are subtracting, this part represents the stator copper losses. So we are subtracting stator copper losses from the stator input. And then we are subtracting stator core loss, RC component. So then we'll be getting air gap power here. That is PAG or rotor input power. From this we are subtracting the rotor copper losses. That gives you gross mechanical power output. From that, if you subtract the mechanical losses, you will be getting the shaft power. So the efficiency equal to output by input, that is shaft power by P input into 100. Okay, let's go to the next slide. I have seen in the earlier slide. Talk about the induction machine. Of course, we have copper loss. Right? The copper loss in induction machine is given by 3 times rated current square into R01. So R01 summation of R plus R2 dash rotor resistance refer to the primary. Okay. And the copper losses at X full load equal to square times full load copper losses. So this is a full load copper loss. Okay. And next we have core losses. Core losses are classified into hysteresis loss and eddy current losses, right? So earlier we have seen in transformers that the hysteresis loss is proportional to B max to the power 1.6 NF, and eddy current loss is proportional to B max square F square, right? Suppose if the ratio, if V by F ratio is constant and V by F ratio is not constant. If the ratio V by F is constant, V max is constant, then hysteresis loss is proportional to frequency. V by F ratio is not constant, then we have to substitute V by F in V max place, then we'll be getting hysteresis losses proportional to V square. And similarly, the eddy current losses in V by F is constant, his eddy current loss is proportional to frequency square. If it is not constant, that is also proportional to voltage square. Okay. See some previous year questions based on the machine equivalent circuit. So this is what we have discussed in the earlier slide. When B by F ratio is constant, hysteresis losses is proportional to frequency, whereas eddy current losses is proportional to frequency square. When V by F ratio is not constant, both losses are proportional to voltage square. Let's try to solve this question. So the figure shows an equivalent circuit of an induction machine, single phase induction machine. So they have given us some parameters like R1 they have given 12 ohm, XL1 is 12 ohms, XM is 240, so 240 by 2 is 120 ohms, and S is a slip. At no load, motor speed can be approximated to the synchronous speed. So slip we know that NS minus NR by NS. They are saying that at no load, NR is approximately equal to NS. Slip is 0. So this becomes infinite, right? Infinite means this circuit is open circuit, so there won't current flow. And here XL2 dash, it is a function of S. So it is multiplication. Here we will be having a function of S. If S is 0, so this will become 0. So here it will be open circuit. So if you draw now the resultant circuit, it will look like JXL1 now JXM by 2 now short circuit XM by 2 by 4. So the equivalent impedance Z equal to R1 plus JXL1 plus. Here you have to take the parallel combination. Of R2 dash by 4 and AXM by 2. You substitute the values of R1, XL and all, you'll be getting around 35 at angle 83 degrees. Now what they're asking is the no load lagging power factor. Now the current I can be given as voltage. Let's say voltage is at angle 0, so V by Z. So we don't know V, so let it be. So this is 155 at angle minus 83.7 degrees, right? Now the power factor can be given as cos of 83.7. That is equal to 0.1. Let's go to the next question. A delta connected 3.7 kilowatt, 400 volts, 3-phase, 4-pole, 50H squirrel cage induction motor. The following equivalent circuit parameters per phase refer to the stator, that is R1 equal to 5.39 ohms, R2 equal to 5.72 ohms, X1 and X2 are 8.22 ohms. Neglecting the shunt branch parameters, they are asking us to find out the starting line current in amperes when connected to a 100 volts 10H source. specified that the rotor parameters are referred to the stator. Okay, and now initially the machine is a 50 Hz machine. Now they are connecting it to a 10 Hz source. So when the source frequency is changed, only change will be in the reactance, right? So the resistances they have given R1 3.72. So frequency is changing. Only the change is X1 comma X2 will change. They are proportional to frequency. So X1 new equal to X1 old 4. So that is old is 8.2. New is 10 by old is 50. So that is 1.64 ohms. Similarly, X2 new is 644. So current per phase is given by voltage per phase by square root of R1 plus R2 whole square plus X1 plus X2 whole square. Per phase is 100. 72 square plus 4 plus 64 square 63 amps. This is per phase current. It's given by I phase. Let's go to the next topic, that is torque production in an induction machine. We know that the power equal to torque into omega, where omega is 2 pi ns by 60. Now torque equal to P by omega, so that is P into 60 by 2 pi ns. The power is nothing but the rotor input power, that is air gap power. So that is 3 into IR square R2 by S to 60 by 2 pi ns, right? So that is torque. So if you take some of the constants in this equation, we can write torque equal to K into, okay, we know that the rotor current equation can be given as IR equal to SC2 by our R2 square plus SX2 whole square, right? So IR square equal to S square E2 square by R2 square plus SX2 whole square, right? And right, K into IR square is S square by square plus SX2 whole square. Then we have one more term. Here we have R2 by S, remaining all are constants. So we'll be having K S R2 E2 square by R2 square plus SX2 whole square Newton meter. So this is the expression for torque. Now let's try to find out the maximum torque developers. The maximum torque is given by T max, which is possible at slip S max. It is given by R2 by X2. So T max equal to K S max E2 square by R2 square plus SM square X. So if you substitute SM here, approximately we can write T max equal to K into E2 square by X2 square. There is one more term called stalling speed. Stalling speed is a speed of the induction machine maximum torque. So generally we know that NR equal to NS into 1 minus S, right? If this becomes SM, the corresponding speed is called as stalling speed. So that is NS into 1 minus S. So we have maximum torque. This is the general torque expression. Now the starting torque is given by starting at the time of starting. We know that the slip is 1, right? So I can write starting torque equal to K E2 square R2 by R2 square plus X2 square. If you see here, the torque expression, starting torque is proportional to rotor resistance. So that's what we have seen earlier, right? In a squirrel cage induction machine, the rotor resistance is high. That's why the squirrel cage induction machine has better starting torque when compared to that of an induction machine. Let's go to the next slide. What we have seen in the earlier slide. that Sm equal to R2 by X2. This is the slip corresponding to the maximum torque, and the starting condition slip equal to 1. Therefore, R2 equal to X2. So the condition satisfied to obtain the maximum torque is rotor resistance equal to the rotor reactance. On derivation, we know that the full load torque equal to Ks 2 square R2 by 2 square plus Sx2 whole square. At the same time, we also got maximum torque expression equal to K times 2 square by 2x2. We also got starting torque expression, that is K times 2 square R2 by R2 square plus x2. Now if you take the ratio T full load by T max, this is given by 2a by 1 plus a square, where a equal to R2 by x2. R2 by x2, okay, for squirrel cage induction machine. But if it is a slip ring induction machine, because since we have slip rings on the shaft, by means of slip rings, generally an external resistance can be added. So we'll be having R2 plus RE by X2. RE is an external resistance. Okay, let's go to the next slide. So this is what we have seen in the earlier slide. Now talk about the induction machine torque versus slip characteristics. torque is proportional to slip. For high slip region, T corresponding to S max is T max. So whenever the mechanical load on induction machine increases, what happens? So which decreases the slip. As slip decreases, the current drawn from the rails increases, thereby increasing the electromagnetic torque till this region is. Go to the next slide where we'll be seeing the torque versus slip characteristics with varying supply voltage. So now when the supply voltage, so let's say the supply voltage is decreased. So what happens when similarly the so supply voltage moves down. See the torque versus characteristics with this is T max. Now what we know that S max is given by R2 by X2. I'm adding external resistance to the rotor. So R2 will increase. So what happens? SM will move in this direction. So this is mu SM. So let's say SM2. Similarly, we also know that the starting torque is proportional to R. So R2 increases, starting torque increases. So this is TST1. So new starting torque is TST2. So the curve will look something like this. Okay, we'll solve some of the examples. So this is what we have seen, the torque versus slip characteristic varying voltage as voltage keep on increasing, torque versus slip characteristic keeps coming down. And this is the torque versus slip characteristic varying rotor resistance. So let's try to solve this question in year 2015 question. The per-phase equivalent circuit of a two-pole three-phase induction motor operating at 50 H. So the air gap voltage across magnetic inductance is 210 volts RMS, slip is 0.05 ohms. So now they're asking us to find out the torque produced by the motor. Let's say this current is I2 dash. Can write I2 dash equal to, they have given the voltage across this shunt branch is 210 volts RMS. 10 by square root of 0.05 by slip. Slip is also 0.05, so this becomes 1 ohm. 0.05 by 0.05 is 1 square plus 0.22 square. So if you solve this equation, we'll get 206 amps. They have given P equal to 2, frequency equal to 50 Hz, and Ns equal to 300 RPM. Sorry, 3000 RPM, 120 F by P. So we know that the torque produced can be given as 180 by 2 pi Ns I2 dash square into R2 by S. Okay, so that is 180 by 3.14 into Ns is 3000 to I2 dash square, that is 206 square into R2 dash, that is 0.05 by 0.05. So this gives you 401 Newton meter. Let's go to the next question. The 400 volts 50 H star connected three-phase squirrel case induction motor is operated from a 400 volts 75 supply. So they are changing the frequency of supply. So torque the motor can now provide while drawing the rated from the supply. So the only change is in the frequency. So we know that the torque provided can be given as 60 by 2 pi plus into P IR square into R2 by S, right? So right torque is inversely proportional to slip. So they are saying the rated current from the supply. So we know that Ns equal to 120 F by P. So frequency increases, Ns increases, torque decreases. Okay, let's go to the next question. The power input to a 415 volt 50 H 6 pole three-phase induction motor running at 975 RPM is 40 kilowatt. The stator losses are 1 kilowatt and friction and windage losses are 2 kilowatt. They're asking us to find out the efficiency of the motor. Power input equal to 40 kilowatt. Stator losses equal to 1 kilowatt. Windage losses equal to 2 kilowatt. This is the stator input. So the stator output equal to 40 minus 1 kilowatt. That is stator loss. That is 39 kilowatt, which is nothing but the rotor input. The gross mechanical power output is given by rotor input. That is PAG into 1 minus S. PAG is the air gap power, which is a rotor input. Slip equal to NS minus NR by S. NS is 1000 RPM minus NR is 975 by 1000. That is 0.025. So PAG is 39 kilowatt into 1 minus 0.025. So this is 38.02 kilowatt. Now the efficiency is given by net mechanical output by input. Net mechanical output equal to the area gross mechanical power output minus windage loss. So that is 38.02 minus 2 kilowatt. That is 36.02 kilowatt. So efficiency equal to output, that is 36.02 by input is 40. So that is equal to 90%. Okay guys, that's all for today's class.